So what is metastable zone width? Yeah. So if you open any textbook, what it states is like metastable zone width is something that can provide information. So it provides information for developing a well-controlled crystallization process. So what does that mean? It's not easy to to imagine or understand if you have a statement like that. Yeah? So what I'm going to do is like we are going to do some experiment, something like your solubility experiment. But this time we are going to add a turbidity meter into the crystallizer. So as I said, the solubility line is something like a heart of the crystallization process. If you don't know anything about solubility, you forget thinking about crystallization. Yeah. So I will try to draw the solubility line again. So you are going to see the solubility line again and again until we finish this topic of crystallization. So you have temperature in the x-axis, let's express in degrees centigrade, and your solubility concentration on the y-axis, so expressed in terms of grams per liter. So let's draw our solubility line. As I said, the solubility line says that your solubility is increasing with respect to temperature. So let's give some numbers on this one. So let's have, this is 30 grams per liter. So if we draw a line here, y you will read 30 grams per liter. And then, so 30 grams per liter is the amount that you can dissolve at 40 degrees centigrade. Let's assume that we are dissolving at the moment, or not dissolving, we are dealing with some active pharmaceutical ingredient whose solubility is 30 grams per liter at 40 degrees centigrade. So this is one condition. And then we know another condition, which is like at 20 grams per liter. So we have at 20 degrees centigrade, we can dissolve the maximum of up to 20 grams per liter, or in other words, the solubility concentration at 20 degrees centigrade is this number, 20 grams per liter. So this is solubility value at 40 degrees centigrade. So I said to you before, like we did some experiment, like imagine you have a crystallizer, you have some solvent, and then you have some API molecule, so something like 30 grams per liter. So what we do is like how we prepare the supersaturated solution. Say we heat, say up to say somewhere around 50 degrees centigrade, and then which means everything will be dissolved. So we are giving this extra bit of temperature to ensure complete dissolution. I will repeat again. So if you project this solubility line at 50 degrees centigrade, you can dissolve even more amount of your API compound. So which means at 50 degrees centigrade, you can very easily dissolve 30 grams per liter. So by heating your solution to 50 degrees centigrade will ensure complete dissolution of your compound, and then you can cool it back very rapidly until 40 degrees centigrade. So this is your saturation temperature. And then before we did an experiment where we try to cool, we will cool the temperature at some fixed cooling rate, say like 1 degree centigrade per minute, and then we cool it until 20 degrees centigrade. That's what we did in the previous experiment. But what we are going to do now is like just to follow the, let's put some, just to follow the blue line which I'm drawing now. So we started at 30 degrees centigrade at this point, and then we are cooling the solution at a rate of 1 degree centigrade per minute. But this time we are going to continue cooling, cooling and cooling and cooling. One more thing I forgot to mention, when you are doing this experiment, this time we added a turbidity meter inside the solution. So this is your turbidity meter. So what is this turbidity meter will do? It's like, imagine you have a clear solution. You know how to make a clear solution. So we heat it to 40 degree 50 degrees centigrade, where you can dissolve all the 30 grams per liter, and then we are cooling back. When it's at 40 degrees centigrade, this solution will be a clear solution, and your turbidity meter will see will say there is no solid concentration, yeah? Which means zero solid concentration. So your turbidity meter is going to say, is going to, how do you call it, it's going to check the optical density of your solution. So if it's more turbid, it will tell it's more turbid. If it's less turbid, it will say less turbid. Or the so or if there is sudden change in your solution, say like you have a clear solution and out of nowhere if it suddenly become a cloudy solution, then your turbidity meter will have some new reading. So that's the basic idea to put your turbidity meter, and then we go back to the same experiment. So we added 30 grams per liter. So this is the your solubility concentration at 40 degrees centigrade, and then you heat the solution to 50 degrees centigrade. So this will ensure complete dissolution. Just assume we have some agitation unit in the crystallizer, so that will help to mix the things so fast. So you heat it to 50 degrees centigrade. We can wait there for 45 minutes. So just to make sure all these 30 grams per liter are completely dissolved in your solvent, and then you cool back. You cool back the solution back to your 40 degrees centigrade. So third is like so cool back from 50 degrees centigrade to your saturation temperature, which is nothing but 40 degrees centigrade. And then from there, the fourth step, we will cool the solution. We don't fix an end point. We will just cool the solution. We will cool the solution at a fixed cooling rate, say like 1 degree centigrades per minute. So when to stop this experiment? So we will continue cooling the solution from just to follow the highlighter now. So we will continue from here, this point, this point, this point, this point, this point, this point, until some point. So at this particular temperature, we don't have to worry what's the temperature at the moment. So at some stage, your solution turns into turbid or cloudy solution, because something happened in your solution, probably some crystallization. Due to crystallization, your solution changed from clear solution to turbid, which means you managed to form some new crystals in the solution, and you just draw the line down. Just as we can, for the moment, we assume your solution turned from clear to cloudy solution at 5 degrees centigrade. So for the set of starting conditions like 30 grams per liter, which is nothing but your solubility at 40 degrees centigrade. So that's your starting point. So let me change the color again. So just follow the pink line. So that's your starting point, and then that's the point. This arrow that gives some number like point A, and this is the starting point B. So the difference in this temperature, we call this as a metastable zone width. So what it says, what, or at least what you can understand from this experiment is like, so when your solution is from 40 degrees centigrade, you are cooling back to 30, 30 to 20, 20 to 10, and then to 5. So throughout this process, your solution remains clear. So which means there is no formation of any solid phase. So which means you can call this like the temperature at which your solution remained clear, which means you are in liquid phase and you are in liquid phase. So that's the meaning of that. I don't know how to say it. So you start from 40 degrees centigrade and you go to 5 degrees centigrade. your solution remains intact, which means there is only one phase inside your reactor, which is a liquid phase, and there is no solid phase. And the solid phase start to occur only when you hit this particular temperature, which is 5 degrees centigrade in this experiment. So the difference, this temperature difference, so T saturation temperature minus the temperature at which your solution change becomes cloudy. If you, many people call this as cloud point, or few people call this as a point of nucleation. So I will explain what is nucleation very soon. So this difference is called metastable zone width. So metastable zone width is extremely important. So this is one experiment we did. So we did only one experiment. We can do obviously many experiments like that. So just I will tell how to do that. So this, I need to go this topic very slowly because it's very tough topic to understand, and many textbook for some reason they are not explaining it clearly. So you have your temperature degrees centigrade in the x-axis, your solubility concentration grams per liter on the y-axis. We know how to perform a solubility experiment. So this is your solubility line. Say this time, so this is a point 30 grams per liter. Just assume, just draw a line, say T1. So what it means, like T1, at T1 your solubility concentration is 30 grams per liter. So if you make a table like a temperature degrees centigrade versus your solubility concentration, so at T1 your solubility concentration will be 30 grams per liter, and then as usual you have to heat the temperature. So heat some temperature like T1 plus 20 degrees centigrade, and then wait at that final temperature T1 plus 20 degrees centigrade. Wait maybe there for 1 hour. So all these 30 grams per liter will be dissolved completely, and then you cool back the solution as fast as possible to your saturation temperature. So this is your saturation temperature, and then you go back, you cool the solution at a fixed rate 1 degree centigrade per minute. So do something like that, and then suddenly at some point your turbidity meter confirms that your solution changed from clear to cloudy solution. So we can call this as cloud point. So you draw a line down here. Say this is some temperature. So whatever the difference here, let's highlight it. So this part, so that's your metastable zone width for this experiment. So that's your metastable zone width. Obviously you can start one more experiment. Let's start another experiment. Say this is 20 grams per liter. And if you draw a line down here, so say let's call this as T2. So when temperature is T2, your solubility is 20 grams per liter. So now we are going to heat the solution. This T2 plus somewhere here. So T2 plus 20 degrees centigrade. So we are going to heat the solution from 20 grams per liter. So what we are going to do is, like, we start a new experiment. We add 20 gram of our API and 1 liter of your solvent. For the moment, let's assume solvent is water. So 20 grams per liter. So we know 20 grams per liter is nothing but the solubility value at T2. Just to follow the circle. So and then you heat the solution to T2 plus 20 degrees centigrade, and then we cool it back very fast. Once we have a clear solution, we cool back the solution to saturation temperature, which is T2, and then you repeat the same experiment. We cool the solution now at a fixed rate of 1 degree centigrade per minute. 1 degree centigrade per minute, and then at somewhere at this point the solution turned into turbid solution. So you draw a line down there. So this is some particular point here. Yeah? So in this case, in this experiment, so this is your zone width, metastable zone width. So this point, and now we are going to do a third experiment. Why not? Because we are not going to lab. Yeah? So we can draw as much as we want. So now we start something. Say we have like 6 grams per liter here. So let's say this is the solubility value when temperature is T3. So in the table T3, our solubility value is 6 grams per liter. So we cool the solution to heat the solution, sorry, T3 plus 20 degrees centigrade, and then we wait at that final temperature for 1 hour, and then we cool back the solution. Same experiment. So this time we take a crystallizer, we add 6 grams, 1 liter of solvent, and then we are heating the solution to T3 plus 20 degrees centigrade. Wait at that temperatures for say 1 hour, and then you cool back as fast as possible to T3, which is your saturation temperature, and then we apply a cooling rate of 1 degree centigrades per minute until we see a cloud point. So we are cooling back here, and then somewhere around here we see the cloud point. So from, if you draw the line, we can know what is the temperature at which the solution turned from clear solution to turbid solution. So in this third experiment, your metastable zone width is here. So in industries, that's what they do. What if they decided to do some crystallization, they have to decide how to produce crystals, whether to grow the crystals or to produce via nucleation. We will come back to this topic of nucleation. So they need this graph. First they need solubility, and then they need metastable zone width. So we already did 3 experiments at the moment. So let's connect these dots, all these dots. So let's change color. So let's connect all these points. So this blue line is called metastable zone width line. So what we learned out of this experiment is something like your solubility line is just to follow the green highlighter now. Just to follow the green highlighter now. So you started from here, 30 grams per liter, and then we cool back the solution to some point until we reach a cloud point. And again the same for the second experiment. We started from 20 grams per liter and then we cool back to reach somewhere here. So when I am talking, I'm also drawing something. So try to keep a note, so where I am drawing. And then this is your third experiment, which is somewhere around here, 6 grams per liter, and then we are cooling the solution to until this point here. So just to follow the green highlighter. Yep. And then if you look at the trend, the solubility trend, it's exponential, and then your metastable zone width line, it will also have some clear trend. Yeah. So what we are going to call this, like the area in between these two lines, just drawing the lines with the green highlight. So we call them as metastable zone width. So what is so special about this? So let me draw the diagram again. The temperature, solubility, the temperature, and then your solubility concentration, grams per liter, degree centigrade. So you have your solubility line and then your metastable zone width line. So anything in between is called a metastable zone width. So what it happens is, like when you heat from this point A, sorry, you cool your solution from point A point B. At point B, you make new crystals. The solution turning from clear solution, so clear solution to turbid solution, which means you already found a significant amount of crystals. Yeah. So metastable zone width will give you some idea. So this is the particular temperature at which your solution is going to become like a cloudy solution, or you're going to, how do you call, you're going to make new crystals from the clear solution. And now and then let me draw something. Maybe I'll go to the next page. I will go it a bit slower. I need to make a diagram bit big. So let's have this solubility line here, and then your metastable zone width line here. Just imagine that's your solubility concentration, that 30 grams per liter. You might expect some problem in the final exam on this topic, so try to pay attention. Yeah, so that's why I'm going a bit slow as well. So you have some point which is at 30 grams per liter, as I said. So this is your metastable zone width line. Just draw the, and just assume for the moment this one happened at 40 degrees centigrade, and then you reach this cloud point, and then you just draw the line down. So this happened at 15 degrees centigrade. So these are some random numbers that I selected. 15 degrees centigrade. And if you look at the solubility line somewhere around here, so let's think at 15 degrees centigrade, your solubility value is 20 grams per liter. So you started your experiment at your saturation temperature with the API concentration which is equal to the solubility at the saturation temperature. So 30 grams per liter, and then when you started from 30 grams per liter, you reached a cloud point. So you draw some line down here. So you reached some temperature, and that particular temperature where you reached the cloud point, the solubility value is 20 grams per liter. 20 grams per liter. So at this point, let's say point A. So if I ask you to calculate the supersaturation ratio, so you can easily calculate. Supersaturation ratio is nothing but C divided by C star. So you just draw the line down. So at this point A, if you draw the arrow down, so maybe I can show by highlight. So this is your point A. So just draw the line down. So that is at 15 degrees centigrade, you reach the cloud point. So at 15 degrees centigrade, the solubility value is 20 grams per liter. So your supersaturation at this point, at this particular temperature, when your solution reached into turbid solution, will be nothing but equal to your concentration 30 grams per liter divided by the solubility value at the temperature when your solution changed from clear to turbid solution. In this case, is at 15 degrees centigrade, and at 15 degrees centigrade, your solubility value is 20 grams per liter. So put that value here. So grams per liter cancel. 3 by 2, it's 1.5. So supersaturation ratio is 1.5. I hope you all follow this one. Thirty divided by 20, 15 degrees centigrade. So everything looks fine to me. And then, so what we learn from this instrument, from this experiment, is like or why industry people call this like a metastable zone width. It will give you information about at what process condition we can control the crystallization process. So what is that? What do they mean by this? So if you start your experiment with 30 grams per liter from the solubility curve, you know we need to heat the solution something more than 40 degrees centigrade. Just to follow. If you start your experiment from 30 grams per liter, we need more than 40 degrees centigrade to dissolve everything. And then if our supersaturation ratio, if you start something at 30 grams per liter, and if your supersaturation ratio is greater than or equal to 1.5, it is more likely that we are going to make new crystals via nucleation. So I will tell what is nucleation in a moment. So nucleation is whatever the thing which is happening, like turning off your clear solution to cloudy solution, which means you form a lot of crystal nuclei inside the solution, and that process itself is called nucleation. But I will try to explain it in a better way. What is exact? Why do we call even this process nucleation? We can call this process again like a like a solid formation. But why we are calling it as nucleation? There are a lot of good reasons to say that. So this is something you have to understand. So whatever I said to you, keep this in the mind. So this metastable zone bit will give you some idea about the point. Like if you start from 30 grams per liter, from the solubility data, we know what is the saturation temperature for that particular concentration, 30 grams per liter. And then we know how to heat the solution. And then we know if we start from 30 grams per liter, if we reach the supersaturation to more than or equal to 1.5, we are going to nucleate the solution. So, and then I said to you, metastable zone width, the industry people, they call this graph, it provides information about how good we can control. Yeah? It will give some information about the process conditions that we need to maintain, where we can control the crystallization process. For industry people, controlling the crystallization process means you have a crystallizer. For them, controlling means they have to control the particle size, and they like to know the number of crystals inside. So they don't want, like, imagine you crystallize something and then you have like a, say like a 10 percentage of crystals at 80 microns, and then 20% crystals at 100 microns, and then say like again 10% at 200 microns, and then say like 50% of crystals at 250 microns, and then say like whatever the remaining percentage, that will be equal to like 300 microns. So they don't like this. Say they don't want this, because this one will affect your flow properties. It will affect your flow properties, and then it's also going to affect your filtration. When you're going to filter, if you have like a larger particles and all the particles remain in the same size, it's easy to filter, and also it's easy to dry, and many other good things, and it's also easy to flow as well. If you maintain, imagine if you can maintain the particle size, so which means you can design everything that comes after the crystallization experiment with some process parameters, where your filtration will be perfect, where your drying will be perfect, and then the flow property will be perfect. So they want some controlled conditions, so where they can control the crystallization experiment. So they don't want this one, and exactly this is what happens when you nucleate your solution. So just to go back to the same graph, just let me change a new color. So just to follow the red arrow, You start your experiments at 30 grams per liter, and then you cool back to point A, which is here. Your solution will change from clear to cloudy solution, and then if you give enough time, the crystals will grow until your concentration reaches 20 grams per liter. So that's your solubility point. So what it will happen, like, so 10 grams per liter, 30 minus 20, so 10 grams per liter will be crystallized. And if you check the size prop, how do you call the size of the crystals, we can check even using a normal microscope, and then we can even calculate the size fractions. And if you see that one, you will see some graph like this, something like we. And then another issue is we will never know how many crystals we formed at this point. The solution is completely cloudy, which means you might have a millions and millions of millions of crystals, yeah. So which means you already lost the control over the number of particles, and you also don't have the control over the size of your final crystals, and you also don't have control over the size distribution of the crystals. And company industry guys, they don't like it, yeah? so so what they need is, like, they want to identify some conditions, or they need to know some process conditions where they can grow crystals, but without the formation of any nucleation. So they don't like nucleation in many experiments. So they need some conditions. So how to identify those process conditions? So I will show you quickly now. So we already know what is solubility line, we already know what is metastable zone width. From this graph, we can easily pick the record level of process conditions where you can completely eliminate the nucleation process, but we can grow the crystals at that condition. So I know I'm going very slow because, but I know this concept itself is very difficult, yeah, and you might have some problem on this topic in your final exam. Probably at once we solve this one, once I finished explaining what is metastable zone width and how to identify the best process condition where we can eliminate nucleation, then I will try to design some problem, and then I will try to solve it right now. Yeah. So so then you might get some idea what really happens when we perform a, but not what really happens, like, what industry people really need out of crystallization process, and how they deal with this process based on the theoretical knowledge which they have, yeah. So for that, if you are going to crystallize a compound, you should know what's the benefit of nucleation, what's the benefit of growing the crystal, and when to go for nucleation, and when to go for a normal crystal growth. So how to identify the best conditions where we can eliminate nucleation? You have your temperature degrees centigrade, and then you have your solubility. So we are drawing this graph again and again. So it's not a mistake because we are learning about crystallization. If we don't have solubility, we cannot learn about crystallization. So we have your solubility line. So we have our metastable zone width. So I'm just going to draw again. So 30 grams per liter when your saturation temperature is at 40 degrees centigrade, and your cloud point temperature, what's that? Let me check. So cloud point is at point A, and then it happened at a temperature of 15 degrees centigrade, and at 15 degrees centigrade the solubility is 10 grams per liter. So what we need, so you have a solubility line, that's your solubility line. Just follow the green highlight. That's your solubility line. And then just follow the red highlighter. So that's your metastable zone width. So what we are going to do is we are going to draw a line somewhere in the middle. So just follow the blue highlight. So what they in industries they do is like what I'm going to explain now. That's how they will identify the conditions. Even in the lab, that's what I do. If I need to grow some crystals and if I don't like to see nucleation inside my reactor, so we know this 30 grams per liter, and we know that the saturation temperature 40 degree centigrade. So this time I will cool back until to this middle point. Say let's call this point B, and then you come down. Say let this point meets at 20 degrees centigrade this time, and then the solubility at that 20 degrees centigrade say is for example 15 grams per liter. So what we need to do is like we create some solution 30 grams per liter, we cool it back to the point B, and then at point B what we have is a supersaturated solution. At point B we have a supersaturated solution, but the nucleation can be least expected or least likely. So if we are in this zone, let me highlight it one time for you. If we are in this zone, like just follow the blue highlighter. So this zone, it's a, if you want we can call it as a safe zone. Yeah, like the chance for nucleation is very less in this zone. So chance for nucleation is very less, or if you want you can say like the probability of the solution to nucleate is less. But when your solution is at point B or somewhere, let's change the color. So if you are in this green region, you have more chance. Sorry, yellow highlight. So you have more chance of entering into the nucleation zone, and above this line, definitely the solution will nucleate. So it's not a, so that's how the industry people, if they want to grow some crystals, so they will maintain the supersaturations. They have to select a supersaturation within this range. Just follow the line. So if they start at 30 degrees centigrade, they have to come to point B, and that's it. They should stop the cooling process. So your final temperature should be whatever the temperature at point B. So that's how the industries they choose the process conditions. If they decided to like like if they want to nucleate, they work at the limit of the metastable zone width. If they want to grow the crystals, they work at temperature very closer to your solubility line. So let me draw one more time. I'll quickly show this one. So if you start somewhere here 30 grams per liter, this is your some middle line, we can call that. If you want to nucleate, we work at this point at the limit of metastable zone width. So whatever the temperature here, we can cool up to this particular temperature, say T1. Or if you just want to grow the crystals, we have to cool the solution up to this particular point, say T2, from 30. So 30 degrees centigrade says at 40 degrees centigrade. That's your saturation temperature. So you cool the solution from 40 degrees centigrade to T2 and stop it, and then you add your crystals. I think I'm going very slow. Maybe hope chemical engineers, they won't fight with me. But this textbook, they won't explain. They won't explain like all these details, like all they say is like what is a metastable zone with, what is a primary nucleation, what is solubility, how to get solubility, what is saturation, what is supersaturation ratio, different types of how do you express supersaturation in different form, and that's it. Yeah, so and they will tell like you have to work near your solubility line, you have to work near your metastable zone with line in case if you want to grow the crystals, or in case if you want to create some new crystals via nucleation. So but but to know the inner details, we have to go through like this. Yeah, it's bit very, I know it's going very slow, but at least you will understand what the crystallization is all about, and how to pick the best process conditions where you can grow some crystals. And soon I will tell like why do we need to grow crystals, and why do we need to go for or when do we need to go for nucleation. Yeah? So these are the things you have to learn, you must learn, and you must understand. Yeah? So at the moment we are not even talking about theory, at the moment we are talking about the experimental facts, how we perform the experiments, and if we perform the experiments, how the outcomes will look like, and what we have to understand from the experimental outcomes, and how we have to use the or exploit the experimental outcomes. Like solubility is one experimental outcome, metastable zone width is one experimental outcome, and we know how to do that now, and we are exploiting that graph in order to find the perfect process condition where we can avoid or even eliminate the nucleation process. And we already know if you work at metastable zone width, we can easily nucleate the solution, which means you can make some new crystals from the solution. So these are some things you must remember. So since I talked about this metastable zone width, and then when like the temperature at which your solution changes from clear to cloud point, so it's good to introduce a primary nucleation. So primary in the exam you have only 40 marks. Yeah, so the remaining 60% comes from your two lab reports. Yeah, so but that 40 marks you have to work hard. Yeah? Last year the pharmaceutical chemistry students, they got more A grades than the engineering students. Yeah, so I think this model have some provides some perfect balance for both engineers and also for the pharmaceutical chemistry students. Yeah, and I am going crystallization process like this because this is some one unit operations that you are going to use somewhere in your life. Yeah, and you must know all these basics. If you go to industry with the textbook knowledge, you will be completely lost. Yeah, so you have to know how they do the experiment, how we do the experiment, and how to get this data, and how to interpret this data. Or if you want to manufacture some product, you have to know this metastable zone width. I will tell you quickly why is that. Yeah, like especially when we manufacture when we are going to deal with some chiral compounds and few other things. Yeah, I will come back to that later. For the moment, let's see what is primary nucleation. So draw your solubility line, draw your metastable zone with line. So you start from some point, saturation temperature, you cool the metastable zone with, you form a new crystals. Yeah, so you start from a clear solution, and then from the clear solution you make a new surface, and then a new volume. So this is nothing but we call it as primary nucleation. So this is what, at least for me, this is primary nucleation. Yeah? So what really happens when in primary nucleation is like, you have, just imagine you have some, you are at saturation temperature and you have some solubility concentration. Your concentration in the solution is exactly equal to your solubility concentration. So let's assume this red are your solute and then blue are your solvent molecules. So when you cool down the solution, what happens is like you're creating a supersaturation. So when you are creating your supersaturation, your solute molecules, they come together. They come together. In fact, to be precise, it won't come together just like that. Yeah, so they will randomly come together like that. There won't be any pattern, and then they will make something like a blob. We call this as how do you call, like solute clusters. Few people call them as intermediate phase. Solute clusters is the correct terminology to use. And then after some time, what all these solute clusters which are clubbed together, they will recognize themselves and then they reorient and reorganize, and then they try to form a perfect crystal. So what it forms is like they try to organize in a particular way. So they will organize in a particular way, and then and then they will create its own crystal lattice. So if we measure the length, width, and breadth, so they are nothing but lattice parameters. And whatever this, and we call this as a unit cell, and whatever the first unit cell which is created directly from the solution without the help of any external source or any external surface. So you have a completely clear solution, and from that solution, out of nowhere, due to your supersaturation, you manage to form something like a stable nuclei. If you want, we can call the first unit cell, which is formed inside your solution. We can call this as a nuclei. And once you form the first nuclei, just imagine you have your clear solution. And once the first nuclei is formed, just like a magic, out of nowhere the solution will turn turbid. So this one nuclei is more than enough to trigger the solution from clear solution to cloudy solution. So which means you will form at least millions and billions of particles, billions of nuclei within a fraction of second. Within a fraction of second. So this is what we call it as a primary nucleation. So primary nucleation is nothing but you make those primary compounds, which is a stable nuclei, and then and you also make this compound without the presence of any additional surface. So which means you have a completely clear solution. That new surface should be created, and that new volume should be built around that surface. So that's what the primary nucleation is about. I think that's more than enough for the moment. So just I'm having some issues with my tab. I'm going to stop recording and then I will continue again.